Hello everyone. In this chapter, we are going to learn about gases. This is a very small chapter, and there is one guiding equation that you must know. So this lecture is all about properties of gases and coming to the main guiding equation called the ideal gas law. So first, let's start with the properties of gases. These properties are put forward by kinetic molecular theory, and most of these properties are very intuitive. So we assume that gases are made out of very tiny particles, and these the particles are so tiny that their volume is minuscule compared to the volume of the container. So for all practical purposes, the volume of the gas can be assumed as the volume of the container because the volume of the particles themselves is very tiny. And most of the gas container is made out of mostly empty space. You know that gas particles are also in random motion and they collide with each other and also with the walls of the container. But these collisions are elastic. That means there is no net loss or gain in kinetic energy. When they collide, one molecule loses energy, it may slow down, and another molecule may speed up, but there is no total loss in energy during the collision. We call such collisions as elastic collisions. And we also assume that the particles are not attracting or repelling each other. This is called the ideal gas assumption. You must know this. This is a very important assumption because later we are going to derive an equation, not really derive, show an equation that is true for any ideal gas, meaning that is it's true if the particles are not attracting each other. Okay, so this is very important to remember. Ideal means we are assuming that the particles are not attracting or repelling each other. They're moving independent of the other particles. They're not being dragged or sped up because of the presence of other particles in this container. The average kinetic energy of gas particles is proportional to the Kelvin temperature of the gas. There is a direct relationship between the Kelvin temperature and the average kinetic energy. This is basically the equation. Average kinetic energy in a gas of the gas molecules um, in a gas is equal to the Boltzmann constant. This is a constant, and here is the value for the Boltzmann constant. And T is the temperature in Kelvin. There is a direct relationship between the Kelvin temperature. This cannot be Celsius because Celsius is Kelvin plus 273. And since there is an addition here, the proportionality doesn't apply for degree Celsius. This proportionality applies only for the temperature in units of Kelvin. All right, now gases are characterized by four properties. You must remember these because there is an equation later that connects them. The four properties of gases are pressure, volume, temperature, and moles of gas. Let's look at pressure first. What's pressure? Pressure, by definition, is force per unit area. Pressure is not just force, it is force divided by the area. So you can think of it as force per unit area or the concentration of force, how force is concentrated on an area. So suppose you are applying the same force on, let's say you're driving a nail into a wall, okay? One of them is very pointy, okay? One of them is very sharp, and another of them is blunt, okay? You're applying the same force, but the pressure here is greater, okay? The reason is you have smaller area. If the area is smaller, then force divided by area will be a larger number. So the pressure is greater when the nail has a very pointed end compared to it having a blunt end. If it has a blunt end, area is larger, and therefore the force is spread out in a larger area. So force per area is going to be a smaller value. The pressure is going to be small here. All right, so what are the SI units for pressure? So we know that force is mass times acceleration due to gravity, and acceleration can be written as distance over time squared divided by area, and area is nothing but distance squared. Okay, so if you plug in the SI units, the SI unit for mass is kilograms. The SI unit for distance is meters. We have over seconds over time square, and the SI unit for time is seconds. So we can write over second square, or we could also write it as seconds to the negative inverse. Okay, seconds to the negative 2 divided by units of distance squared. Distance in the SI unit for distance is meters, so it's going to be over meter square. Now the meters on the top and one of the meters from the bottom cancel out. So the SI unit is kilogram meter inverse per second inverse square. So the SI units for pressure are kilogram per meter per second square. This is nothing but a Pascal. So we can say 1 kilogram per meter per second square is equal to 1 Pascal, which is denoted by PA. PA stands for Pascal, and that's the SI unit for pressure. Okay. All right. Now, where does this gas pressure come from? What is it due to? The pressure of a gas is due to the molecules colliding with the walls of the container. Okay, they collide with a certain force. So force divided by the area gives you the pressure exerted by the gas molecules per unit area in any container. So that's the pressure of a gas. Now pressure, it doesn't depend on the identity of the gas molecules if you're assuming the ideal assumption that the molecules are not attracting each other. So as long as the molecules are not attracting each other, it doesn't matter whether they're big or small. Okay, the pressure is going to be same as long as they're enclosed in the same volume. So pressure in a given volume does not depend on the identity of gas particles. The reason is we already learned that um, the temperature decides how fast these particles move, or the temperature is what decides the kinetic energy of these gas particles. So it doesn't depend whether these are small or big. The kinetic energy is going to be constant as long as you hold the temperature constant. Okay, so they're going to move with the same kinetic energy, average kinetic energy, as long as the temperature is held constant. That means they're going to collide with the same energy or the same force as long as the temperature is held constant. It doesn't depend on the mass of the particles, because kinetic energy includes the mass. We already learned kinetic energy is half of mass times velocity square. So it includes the mass, and the temperature decides the kinetic energy of the particles, which ultimately decides the pressure, not the identity of the gas particles. Now the pressure in a closed system is constant. So as long as the volume is constant, the pressure of gas inside that container is going to be constant. It's not going to change over time. You're not going to lose or gain pressure inside as long as you hold the volume, keep the volume constant. Okay. The atmosphere also exerts pressure. So the atmosphere is strong enough that if you take out the air from this metal can, amount of air inside decreases and the atmosphere can crush it. Atmospheric pressure is large enough to crush a metal can. We use atmosphere as a standard for pressure, and if you're at the sea level, we call it the normal atmospheric pressure or standard pressure. So you should know this term, normal pressure. Normal means atmospheric pressure at the sea level, which is 1 atm, 1 atmosphere. Atmosphere is a unit of pressure, and as you can see here, there are different units, and 1 atmosphere is basically 101.325 kilopascal. Okay, so atmospheric pressure at the sea level is 1 atm, and it can also be measured, pressure can also be measured in units of millimeter mercury. Okay, you can measure pressure using a barometer filled with mercury. So barometer is nothing but a cylindrical tube that is open at one end. It's filled with mercury, and then it's inverted into a container containing mercury. So now think about what happens to the level of mercury inside this tube. At some point, it's going to stabilize. It's going to stabilize when the weight of the mercury in this tube balances the pressure of air pushing the mercury inside. So think about it. There are two forces that are acting. The weight of the atmosphere, or the pressure of the atmosphere, is trying to push this mercury into this tube. But because of gravity, the mercury's weight makes it come out of the tube. So when these two forces are in balance, the level of mercury inside will stop moving. And if you do this experiment at the sea level, the column of mercury inside this tube is going to be 760 millimeter high. Okay, and that's why we can use this as a unit for measuring pressure. At the sea level, atmospheric pressure is 1 atm, which is the same as 760 millimeter mercury. Millimeter mercury is nothing but torr. So 1 millimeter mercury is 1 torr. This is another unit for pressure. So we can say 760 millimeter mercury is 760 torr. Okay. All right. Now, what is the atmospheric pressure due to? It's because of the weight of the atmosphere above any surface. So if you're standing, there is a lot of atmosphere or air above you, which is pushing down on you due to gravity. So that's what constitutes atmospheric pressure. That's what atmospheric pressure is due to. So if you're climbing a mountain, so let's say you're climbing a mountain compared to when you're at the level ground, okay? The weight of air above you is going to be less on the mountain. So what happens to the pressure? So pressure is low, low pressure if you're on the top of a mountain. And if you're in the valley, then the weight of atmosphere above you is high, so the atmospheric pressure is high. All right. Now you should know these conversion factors. These are very important conversion factors for pressure. 1 atm is 760 millimeter mercury. And in terms of a very familiar unit, pounds per square inch, atmospheric pressure is 14.7 pounds per square inch. Okay, you imagine what this means. Square inch is about the area on your thumb. Okay, it's actually half of your thumb. Okay, an inch square is the area about half of your thumb. So imagine lifting 14.7 pounds on your thumb. That's a lot of pressure, but you don't feel it because your body's pressure inside and outside are in balance. Okay? All right. So this is a very important conversion. 1 atmosphere is 760 millimeter mercury, which is also 760 torr. Most of the time, problems in this chapter involve converting units of pressure to atm. So if you're given the pressure in millimeters mercury, you should be able to convert it to atm. So this is a unit I would encourage you to memorize, this unit conversion. Okay. All right, now coming to STP, what does STP mean? So whenever you hear the term standard temperature or pressure and pressure, which is abbreviated as STP, it means the pressure is 1 atm and the temperature is 0 degrees Celsius, which is 273.15 Kelvin. You must know these terms. When I say normal pressure, you should know that I'm referring to 1 atm pressure. And if I say STP, it means P is equal to 1 atm and T is equal to 273.15 Kelvin. Using just this one equation, PV is equal to nRT, you can derive a lot of other equations that you will be using in this chapter to solve problems. Okay, here we go. So let's say your initial pressure of the gas is P1, initial volume is V1, initial temperature is T1, and let's say the initial moles of gas is N1. Let's say you're changing all these variables, meaning let's say you're increasing the pressure of the gas by putting the gas under water. Let's say your water is at a higher temperature. In that case, the temperature of the gas is also changing. Let's say you are um, you're squeezing the balloon that you're putting under water, under hot water. So in that case, the volume is also changing. And let's say you're also removing gas. The balloon has got a hole, so the gas is escaping. So let's say all these variables are changing for the gas. Now let me call the new temperature, pressure, volume, and moles of gas as P2, V2, T2, and N2. These are your initial conditions, and these are your final conditions. How do we relate them? Well, we can start from this equation, and we can put only the constants, all constants put at one side of the equation. And the only constant here is R, which is the only constant in this equation if all your pressure, volume, temperature, and moles of gas are changing. So if we rearrange this equation to put only the constant value on one side, this equation becomes PV over NT is equal to R, which is the only constant we have. Okay, so that means the product of pressure times volume divided by moles times temperature should remain constant, so regardless of what your pressure, volume, temperature, and moles of gas are. Okay, so we can say in this case, P1 V1 over N1 T1 should be equal to R. And in this case as well, P1 P2 V2 over N2 T2 should be equal to R. Okay, as you can see, this is equal to R, that's also equal to R. So we can equate the left-hand sides in both these equations. So we can write P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. So this is our equation that relates final pressure, volume, temperature, and moles of gas to initial conditions. Okay. Now, what happens when we keep N and T also constant? When we hold number of moles and the temperature constant, you can cancel moles and temperature, and this equation boils down to P1 V1 is equal to P2 V2. Now, what happens to this equation when you hold volume and temperature constant? Volume and temperature constant. As you can see, volumes cancel out. V1 and V2 are the same now, so they cancel out. And the temperatures cancel out. And you can see this boils down to P1 over N1 is equal to P2 over N2. What happens when we hold pressure and moles of gas constant? This equation boils down to V1 over T1 is equal to V2 over T2. And similarly, if we hold pressure and temperature constant, it becomes V1 over N1 is equal to V2 over N2. The different names for what these equations are about. So this is called the Boyle's law equation. And this equation is basically telling you that the product of pressure and volume should be constant, which also means pressure and volume are inversely related. So pressure and volume are inversely related to each other, which is written out symbolically this way. Okay, because if the volume is doubling, the pressure has to become half because their product should be the same before and after. And that's the reason why pressure, we can also say that this equation is telling you that pressure and volume are inversely related to each other. Now, this equation is telling you that pressure and moles of gas are directly related to each other. This is called the Hamilton's law. So basically, what this is telling you is that if you pump gas into a container at constant volume and temperature, the pressure should increase. So greater the amount of gas, greater is the pressure of the gas inside a container. And as you can see, these ratios are telling you that volume and temperature are directly related. So if you increase the temperature of a gas, the volume also proportionally increases to maintain constant pressure. Similarly, if you pump more moles of gas, the volume will proportionally increase if you want to hold the pressure constant. Of course, the temperature is also constant, okay? Now, the names for these two laws, the first one, volume and temperature being directly related, that's called Charles' law. And this relationship is called Avogadro's law. Next, you can use this equation to solve any one missing variable if the other three variables are given. R is a constant, you know its value. So if any other three variables are known, you can always calculate the fourth one. Remember, N stands for moles, and you may not be always given moles in the problem. So if your grams are given, you should be able to change those grams to moles and then use this equation. Alternatively, you could be asked to calculate grams of gas given the pressure, volume, and temperature. So when these three variables are given, you can use this equation to calculate moles and then change your moles to grams. I want to also show you an important consequence of this, what happens to this equation at STP. So at STP, STP means pressure is equal to 1 atm. So we are going to plug that into this equation for pressure, and temperature is 0 degrees Celsius, but the temperature unit that we need in this to use this equation is Kelvin. So 0 degrees Celsius is 273 Kelvin. Now when you have 1 mole of gas, so when your N is equal to 1 mole, so for 1 mole of any gas, that means when your N is equal to 1 mole, you can rearrange this equation now and solve for the volume, because now you know the pressure and temperature, and we are having, if we have 1 mole of gas, your N is equal to 1. The value of R is known, which is 0.08206 liter atmosphere per mole per Kelvin. Now you can solve for V. You can put it in your equation, in your calculator, and solve for V. V turns out to be 22.4 liters. This is called molar volume at STP. So 1 mole of any gas occupies 22.4 liters only at STP. So we can say molar volume of a gas at STP is 22.4 liters. This is just another way of saying this conversion factor. So what does that mean? So let's say you have 4 grams of helium. 4 grams of helium is 1 mole because this is the molar mass. 28 grams of nitrogen is also 1 mole, and 16 grams of methane is 1 mole. So if you have 1 mole of gas at STP, then they all occupy 22.4 liters. They occupy the same volume, okay? Also, another consequence is if you have equal volumes of gases at a given pressure and temperature, it would mean they have equal moles of gas or equal particles of gas. So you should think of this container having, um, let's say if this has 5 moles of helium, it would also mean there are 5 moles of nitrogen and there are 5 moles of methane in these containers. How is that so? Think about it. If you hold pressure and temperature constant, Let's say pressure and temperature are constant for these two. Now, if you hold the volume also constant, if the volume values are also same, then when you use this equation, you're going to end up with same values for n as well in all these three cases, right? So equal volumes means equal moles when their pressure and temperature are held constant. Finally, you can use this equation to derive two more properties, the density and concentration of gas. Let me first show you how to derive the density. So N in this equation stands for moles. We can rewrite moles as grams over molar mass. So I just rewrote N as mass of the gas divided by the molar mass of the gas, because we know that mass divided by molar mass should give you moles. You can check that from the units. Grams divided by grams per mole is going to give you inverse of mole inverse, which is nothing but moles. Okay, all right. Now let's rearrange this equation so that we put mass and volume on one side. So if you cross multiply this, first let's cross multiply. So PV times molar mass is equal to mass times RT. Next, we take mass and volume to one side. So you have to divide this side by the volume. So volume cancels over here. And RT, you bring it to this side. So divide both sides by RT. So the equation rearranges to give you this. Mass over volume is nothing but density. So we can say density, which usually is represented by this Greek letter rho, is equal to pressure times molar mass of the gas. So the capital M here, the uppercase M stands for molar mass, divided by RT. So if you know the pressure, the molar mass, and the temperature of the gas, you will be able to calculate its density. As you can see here, if you bump up the value of molar mass, the density of the gas increases. So density is proportional to molar mass of the gas. If you bump up the temperature, because temperature is in the denominator, this whole value will decrease. So increasing the temperature decreases this whole value, which is the same as saying increasing the temperature decreases the density of the gas. So gas expands, you know that gas expands if you raise its temperature. So which would also mean the density of gas would decrease. The air becomes thinner and thinner as it expands. All right. Um, now, similarly, you can rationalize how pressure and density are proportional. Next, we are going to derive a formula for concentration. So all you need to do is put moles and volume on one side of the equation. So if you take moles and volume to one side of the equation, it boils down to N over V is equal to P over RT. Bring RT to this side and volume to that side. Okay, and N is moles and V here is volume in liters. So you know that moles over liters is nothing but concentration or molarity. So we can say concentration of the gas expressed in molar units, that is moles per liter. I'm writing concentration at C here because we already used uppercase M to represent the molar mass. So this time we are going to represent molarity by C. So molarity is equal to pressure of the gas divided by the gas constant times the Kelvin temperature. So this is the equation that gives you the concentration. As you can see, pressure and concentration are related. So higher pressure also would mean higher concentration for the gas, and you can change one to the other based on this conversion, based on this formula. So here we go. We derived a number of equations using PV is equal to nRT. So most of the challenges in this chapter is writing down what you have, writing down what you're looking for, and then deriving the connecting equation from PV is equal to nRT.